You're listening to Skeptoid. I'm Brian Dunning from Skeptoid.com. Why you need to care about methane. The causes of climate change are important to those seemingly few of us who note that extreme weather events get more common and deadly and expensive every year, that glaciers are permanently disappearing worldwide, that ice sheets at the poles are becoming smaller, that our local weather events, be they flooding, drought, heat waves, or ice storms, are worse every year, that industries like agriculture are being permanently disrupted, and that the economic effects of all these are promising to pile up higher and higher and send us all right back into the Stone Age. And we've probably noticed that among all the talk of fossil fuels, carbon dioxide, the hockey stick graph, and the need to stop burning oil and coal are a few quiet mentions of methane. Sometimes we hear that it's the most potent greenhouse gas of all, which makes us scratch our heads wondering that if that's true, then all the talk wouldn't always be about carbon dioxide and fossil fuels. So today we're going to find out what's up with methane, and what is the latest and greatest state of our knowledge of where methane fits into the climate change emergency, if it even really does at all. The short answer is that it does, and in a uniquely crucial way. As a greenhouse gas, methane actually has a bigger impact on short-term global warming than does carbon dioxide. Each year the atmosphere has more and more methane in it, and that's accelerating warming much faster than would CO2 alone. And one reason that's so crucial is that if we could reverse that increase in methane, such a reversal would do more than anything else to slow global warming. Potentially even slow it enough that we could keep the Earth's temperature from rising above the targets set in the Paris Accords. So, yeah, you do want to care about methane. A lot. Now let's go into the details of why. Here's my best metaphor for the difference in how methane and carbon dioxide affect climate change. Imagine we're all sitting together on a gigantic rocket sled, and the farther that sled goes is how high above pre-industrial temperatures the climate will get. Ideally, we want that sled to be stopped, but it's powered by two big rocket motors into which we keep dumping fuel, and that rocket sled is going to keep going as long as the fuel lasts. One of those motors is powered by carbon dioxide. It has a small nozzle, and so has less thrust. However, it takes a really long time to burn through the fuel. When we add carbon dioxide to it, that motor will burn for centuries with a long, slow, steady thrust. But the second motor is powered by methane, and it has a much larger nozzle. When we add methane to it, it burns explosively, snapping all of our necks back with rib-crushing acceleration. But it burns through that fuel very quickly. Methane that we add to it only lasts for decades. But during that short burn, the methane motor drives us much farther down the track. So in the big picture, carbon dioxide is what really determines our ultimate fate. But in the foreseeable short term, methane is where we have the most ability to throttle between the best and worst case scenarios. So what is it about methane that gives it this great power? Two things: its tremendous effectiveness as a greenhouse gas, combined with its short lifespan. Once it's in the air, a given amount of methane traps 84 times as much heat energy as the same amount of CO2 over 20 years, and 28 times as much over 100 years. That amount drops so much because methane doesn't last very long. A molecule called a hydroxyl radical is naturally found throughout our atmosphere, and this reacts with methane and oxidizes it. Because of this process, and a few other less important processes, methane in the atmosphere has a half-life of about 9 years, compared to carbon dioxide with a half-life of about 100 years. If we can pull back the amount of methane that we're adding to below the rate at which it disappears, we have a unique ability to make a real dent in global warming. So this raises the question of where the methane is coming from. Is it natural, or is it something that we have the ability to modulate? Well, there is both. Various studies over the years have measured this, all with slightly different results, as it's a ferociously complicated thing to quantify. But a good median, and a well-accepted number, is about 600 megatons of methane is added to the atmosphere each year, and about 575 megatons is the amount that's naturally removed. So we're putting in more than is coming out, and that's backwards. Prior to the Industrial Revolution, there was always more than enough natural sink capacity to remove whatever was put in. Of that 600 megatons, about 60% is man-made, and about 40% is natural. The greatest natural source of methane, by far, is wetlands, and other natural sources include termites, the ocean, and ocean floor hydrates. Those ocean floor hydrates have been in the news. They're one half of a potentially very severe methane problem from the Arctic, which has been popularly dubbed the Arctic methane bomb. Methane hydrates are a type of clathrate, which is gas embedded within water ice crystals. These are found naturally in the seabeds under all the world's coldest oceans. Once the ocean water warms just slightly above that frozen clathrate's melting point, well, it melts and releases those gases into the water. Countless gigatons of methane are currently sequestered at the bottom of the northern oceans. The other half of the methane bomb is the permafrost, the frozen mix of soil and organic matter that forms the ground over much of the Arctic. When temperatures are above freezing, it thaws and decomposes, releasing more gigatons of methane. The theory is that with just a little bit of warming, the Arctic methane bomb will release enough methane to make themselves melt even more, creating an unstoppable feedback cascade. It is scary stuff. The reason this has been in the news is that a small amount of data, so far not corroborated, has found that this process has begun. But whether it has or hasn't, the natural sources of methane are out of our hands. So let's look now at the other 60% of methane, the part that's man-made, and see if there's anything we can do about that. Every country produces different amounts of methane from different sources, due to differences in industry, food production, climate, and other factors. So we just look at the total. Worldwide, there are 6 big man-made sources of methane. They are livestock, rice cultivation, waste practices, landfills and sewage management, coal mining, oil and natural gas production and distribution, and biomass burning, basically deforestation. It's this 60% that's been shooting up and has taken us over the sink rate, which means that rocket sled we're all on is opening its throttles to full speed. So the question now becomes whether we've recently changed some practices and gone in the wrong direction, and whether we can reverse that course. We are not without tools when it comes to finding an increased amount of methane in the atmosphere and wondering where it came from. Chemically, methane is CH4, the very simplest of the hydrocarbons, consisting of 1 carbon atom and 4 little hydrogen atoms. If you could set one on the floor, you'd have a tetrahedron, like a 3-legged stool with 1 hydrogen sticking straight up. That carbon atom at the center is the key. Carbon comes in a variety of isotopes, 15 of them to be exact, but only 2 of them are stable, carbon-12 and carbon-13. Overall, on Earth, there are about 90 times as many carbon-12 atoms as there are carbon-13. But every carbon-containing compound has its own particular ratio of the 2, depending on how and when it was formed and through what process. And when we look at all the sources of methane in the world, whether that's natural gas, methane hydrates, permafrost, even cow farts, each has its own identifiable isotopic signature, because each was formed in a different way. What this means is that we can look at the isotopic signature of atmospheric methane today and compare it to the signature of atmospheric methane from 10, 50, 100 years ago, and measure the difference. Combining all the various lines of evidence, we can directly measure what kind of new methane has been added to the atmosphere, both how much and when. Its isotopic signature tells us the source. No guesswork or models needed. And guess what that guilty new source is? Surprise, it's not the Arctic methane bomb. Although the processes that can potentially release all that stored methane are very real, and may indeed happen in the near future, they haven't happened yet. We have no evidence that runaway methane feedback has started, despite some highly publicized fringe reports to the contrary. This leaves us with a little bit of good news. The vast majority of the increase in atmospheric methane has been isotopically identified as having come from oil and natural gas production, the leading human-caused source of methane. A lot of this is leakage during storage and distribution, but the majority of the methane is simply released by the extraction process. While the oil is sucked up the pipes by pumps, the methane in the same deposits just floats right out into the air. With the dramatic increase in fracking, especially since about 2010, such releases have been compounded considerably. Why is that good news? Because oil and natural gas production is the one source of methane for which we humans actually have our hands on the throttle. We could shut it off tomorrow. Obviously, that's not going to happen, but the good news is that we could. Oil and natural gas production is the low-hanging fruit to make the biggest dent in climate change, and it also happens to be the only source over which we have full control. So let's wrap with some tools that every listener can make use of, no matter where you're located. One good place to find the biggest emitters in your country is the Methane Tracker database on the website of the International Energy Agency, an intergovernmental organization consisting of the energy ministers of all its member countries. Now, it's a group that's been criticized in the past for being too friendly on fossil fuel, so I hope that for this purpose we can dismiss any claims of bias. Select your country and see what are the biggest sources of methane emission, and then in your country's elections, vote accordingly. In the United States, it's natural gas that requires fracking. Need to stop it now. In Australia, it's a tie between offshore gas drilling and fracking. In the United Kingdom, it's offshore oil. In Canada, it's neck and neck between fracking and onshore oil drilling. If you're located anywhere else, go to that website and select your country. Then use your vote, and any influence you might have, to limit or terminate those activities. It's not like there aren't better alternatives, and the fossil fuel industry is already a dying one worldwide. It's time to transition to the better choices. It's the right thing to do in every way. A great big Skeptoid shout-out to premium members A. Funk from Halifax, Nova Scotia, Speakeasy Arcade, Mike Marsh, and Jason J.J. Bush. Remember, we always do our best to publish any corrections, so if you find an error in any Skeptoid episode, come to skeptoid.com/corrections to report it, and I'll include it in an upcoming corrections episode. And every Skeptoid episode has a transcript page at skeptoid.com with complete bibliographic references and further reading suggestions. And they also print out into nicely formatted PDF documents that you can share. You're listening to Skeptoid, a listener-supported program. I'm Brian Dunning from Skeptoid.com.